Thank you very much, and thank you very much to the organizers. And thank you also to Thomas for his beautiful talk in which he gave a lot of the definitions that I will need. So this will be a very hands-on talk. So my goal is to begin with some very basic constructions and then end up with, well, a small but non-trivial example which illustrates the theorem with Charles that I want to talk about. So an overly cluttered slide here, but thanks to Thomas, we're talking about codimension 1 co-oriented foliation. So we're thinking about, we have this manifold and it's decomposed as a union of leaves, and you should think about the leaves as typically being non-compact. And a slight difference is that I'm going to be interested in allowing my boundary to be non-empty. And when the boundary is non-empty, you need to specify how you want the foliation to meet the boundary. And so if your boundary is, let's say, a torus, then we're thinking about, oh, I'm not doing this thing very well. Then we're thinking about, well, we can insist that it be tangent to the boundary, or we can insist that it be transverse to the boundary. And then we're going to allow ourselves more complicated boundary components, and then we're going to use these notions of Dehn where we're talking about sutured manifolds. And at the moment, I'm just going to say, okay, we've got some sort of hybrid. We've got parts where where the foliation is tangent to the boundary and parts where it's transverse. We can notice that where it's transverse, we have to be Euler characteristic 0, and so we're only going to have tori and annuli as our possibilities for transverse, because everything today that we're going to be talking about, we're going to be thinking about M is oriented, and we're going to be thinking about the foliation as being co-oriented. And as Thomas mentioned, Caligari has this nice result that tells us if we start with a topological foliation, it can just be, well, if we start with a C0 foliation, it can be isotope to be stealing notation and slightly distorting it from Larry Conlin to be C infinity 0. And that just means that the leaves are smoothly immersed and our tangent plane field is C0. So we're thinking about continuous tangent plane field. Our tangent plane field is defined and continuous everywhere. Okay, so we're going to get sort of really hands-on in sort of visualizing what's going on here. And let's think one dimension lower, and there's a very useful definition. I'm going to call it staircase spiraling. And so let's just begin with, you can think about having two one-manifolds. We've got our circle, and we've got an arc, alpha. And alpha just meets the circle in one of its endpoints. And everything inside is transversely oriented. In our world, we can also think the leaves are oriented. So I've got the transverse orientation indicated by a plus. Think about that. The transverse orientation is pointing in the plus direction, transverse orientation pointing in the plus direction. And what we want to do with this picture that's in the uppermost left is say, oh, okay, let's as an intermediary step add countable number of copies of the curve C. So we can think about the innermost C that we started with is at height 0, and then we've got a circle at height 1 over n for all positive n. And then we're going to say, oh, okay, well, this alpha now intersects all of these added circles in its interior. And so we can do cut and paste, and we can do cut and paste as we've described right here. And so at every intersection, so there's going to be countably many, we're just going to remove the intersection in a way that's prescribed by the orientation. So at the end of the day, we're going to have that single C cross 0 left, but my alpha has now morphed into a curve that spirals in on the C0. And we're going to call that staircase spiraling, or it is called staircase spiraling. So let's think about the ray annulus described using this method. So we're going to have two circles, a single arc, and at each endpoint of an arc, we're going to do this spiraling game around the circle. So we're going to do staircase spiraling around this innermost circle, staircase spiraling around this outermost circle. And after doing this, we're going to have this copy of R, and one end spirals in on the innermost circle, and one end spirals in on the outermost circle. So I'm going to think about describing the Rabe annulus so that's going to be the foliation of the annulus that has two compact leaves, and then an S1's worth of these red leaves that we have over here. And we're going to just think about two-step process. First do this staircase spiraling, and then fill in the complementary region. It's just a product. It's just a digon. So we can fill it in with just parallel copies of that one red leaf. And the foliated annulus we get is what's known as the Rabe annulus.
What do the signs mean?
The signs are the transverse orientations. So we are doing the cut and paste as prescribed, the surgeries, or the cut and paste thing is prescribed by the orientations. Okay, so now we're going to do this staircase spiraling a dimension higher. And so we're going to think about the Rabe component that Thomas also mentioned. And so we're going to begin by thinking about we have a torus and we have a red disk. And then we're going to take countably many copies of the torus and do this same cut and paste game so that we end up with a copy of R2 with its end spiraling around the compact torus leaf. And then the Rabe component is the Rabe foliation of my solid torus. Again, the complement of the black torus and the red copy of R2 is just a product. So you can fill in with just copies of that R2 to get our Rabe foliation. And it's a fact, and there's various proofs of this, but let me cheat. And we know that every manifold has an open book decomposition, or I guess every closed orientable three-manifold we have an open book decomposition. And we can play this game. We can start with the open book decomposition, so we have a solid torus corresponding to the binding, or maybe multiple solid tori, and we've got the pages of the book, so we've got the fibration, and then we're just going to say, oh, okay, that one of those fibers is going to play the role of the alpha. And we're just going to do the cut and paste, so we have spiraling around the boundary of the bindings, and then we're going to fill in the bindings with solid tori. And I'm going to be kind of sloppy, unlike Thomas, and just say, well, foliation is taught if for every leaf L there is a closed transversal to F that meets the leaf. And that's equivalent to there being a single transversal that sees every leaf. And Sue Goodman tells us, and delete this thing that I wrote in here, it's not important for us today. So a foliation is taught if and only if there don't exist dead-end components. So you should think about dead-end components as being generalizations of the Rabe component. We've got some number of torus leaves, and as oriented objects, they cut off an oriented submanifold. So if you look at a component that's cut off by, that's bounded by these leaves, it's bounded as an oriented submanifold. So the co-orientations of the tori all either point in or they point out. So if you want to think about a very concrete notion of what we mean by taught, it's that we don't have any dead-end components. So in particular, taught implies no Rabe component. And Rabeless foliations are interesting enough that they capture interesting information about a three-manifold. If we have a Rabeless foliation in M, we saw in the earlier talk that if M is S1 cross S2, or maybe we did, I forget. But anyway, if we have S1 cross S2, the only foliation is the product foliation by S2s, or the only Rabeless foliation is the product foliation by S2s, which is pretty boring. And so for the rest of the talk, if I talk about a manifold, I'm talking about a manifold that's not S1 cross S2, even if I forget to make that statement. Rosenberg tells us that if we have a Rabelais foliation, we know we're irreducible, as was mentioned earlier multiple times. Novikov tells us that loops transverse to F are going to be infinite order, and pi 1 of m is infinite. And Palmyra tells us that the universal cover is R3. So if we have a Rabelais foliation, we have topologically interesting stuff going on. We can think about trying to put loops transverse to the leaves. We can think about trying to put surfaces transverse to the leaves and see sort of what type of intersection pattern, canceling of centers and saddle type games. And taut foliations capture even more information. So if we know that S is a compact leaf of a taut foliation, then Thurston tells us that it's Thurston norm minimizing. So roughly its absolute value of its Euler class is going to be minimal. And Gerbai gives us a converse that if we have an irreducible manifold and a non-zero second homology class, then there's going to be a taut foliation that has that S as a leaf. Eliashberg, Thurston, Ozhváth-Szabó combined tell us that if M contains a C-infinity taut foliation, then M is not an L-space. And Thomas gave us a lot more details about that. Okay, so here is, we're moving up from thinking about the Rabe component. But again, this is going to be, I can describe this in a staircase sort of way. So now I'm going to think about instead of thinking about just a smooth torus, I'm going to think about taking this polygon, and let's at the beginning just go across S1. So we have a solid torus, and you should think about those purple annuli. Really, this is something that's sitting inside a manifold, and the leaves are, I've got leaves that look like these black curves across S1, but then they're heading off into my manifold and doing whatever they're doing, but the arc here is cutting off, the two leaves are getting exponentially closer as we head off to infinity. So I'm going to refer to, so at the moment I'm going to just say, oh, okay, let's look at this first M. And M cross S1 looks like this. It's a solid torus with these purple arcs turning into annuli. And I'm going to think about, take a meridian disk, except, and that's what's marked in red here, except I'm only going to do this staircase spiraling away from the purple. So I'm going to think about taking countably many copies of the annuli that are corresponding to the white region, and then just do this oriented cut and paste and have spiraling. So if you think about what's happening, we're going to get this saddle on the inside, where two of the ends of my saddle spiral in on this piece right here, and the other two spiral in the opposite direction. And on the purple, we're going to see, the leaves that spiral into the boundary of the purple. So this is a game that's been known for a long time. Thurston, Juhász, maybe some others I should be naming. And it's known as stacking chairs. So you can think about what we've got in this solid torus. We have the game we had before. We have one leaf, and then we add in a bunch of parallel copies of that leaf. Okay, so here is a picture of a special case of that. Well, if I think about that as being defined well enough. So here's another example of a similar sort of thing. where I'm thinking about the blue is bounding a solid torus with these cusps. So you can think about, we've got these annuli heading out along where the blue spiky things are happening. And we're thinking about K as being a knot just in the core of that solid torus. And then we're going to think about doing Dehn surgery along K. And we know if we do Dehn surgery along a core of a solid torus, we just get a solid torus back. And so we're going to have changed the slopes. So we're going to think about our new I'm going to think about giving this blue torus the blackboard framing. So those cusps are at slope 1/0. They correspond to, if I'd been drawing these purple annuli again, I would have had 2 purple annuli cutting off those ends. And so if I do P/Q surgery, I'm going to get a solid torus back. But now my meridian disk is going to intersect the slope 1/0, these guys, 2 times the absolute value of Q times. So that tells me that I can play this stacking chair game as long as Q is not equal to 0. So another way of thinking of this is that I can give you a foliation of the interior of this blue so that it's going to meet the boundary of a neighborhood of K in slope P/Q. And so I'm going to have taut foliations that restricted to this object that realize every slope P/Q except the one that corresponds to Q equals 0. So Q equals 0 is bad. It means I'm doing a surgery. I've got a compression of my blue torus, but anything else is going to give me a nice foliation of this solid region. So now think about that blue thing as just lying as a sub-object. I've got some, I was hoping I could avoid talking about branch surfaces. Yeah.
So in the previous picture, so your 2 cusps are the meridians on top and bottom?
So my 2 cusps correspond to, here's one and here's another. So we have, so I should think about, so if I think about this curve right here, I could think about cutting off here. I've got a circle that somehow I can't handle this little red thing very well. But I've got a circle here, and I've got another circle. Okay, so how many people here know what a branch surface is? How many people don't know what a branch surface is? To figure out, okay, so I've been cheating a little because I was hoping to not talk about a branch surface, but a branch surface is just an object that, it's a 2-dimensional object in which every point has one of the following 3 neighborhoods. So we can think about these surfaces that are the leaves of my foliation, or tend to be non-compact. And so we would like a compact object that lets us grab hold of the leaves in some reasonable way. And if we go back to the earlier examples, maybe even this one, you can think about, you begin with, actually let's go all the way back to the Rabe component. Maybe even this one. Okay, so if you think about this annulus that we had, we started like this. We ended up like this. But an intermediary object would be, well, it's way easier to draw this intermediary object than it is to draw this one over here. So we have a compact object that in some very strong sense is telling me, what those transverse orientations told me, and it's telling me that really I'm seeing leaves that look like this. So if we go up to the next example, now we're thinking about a branch surface where intermediary between the one on the left and the one on the right, I would have a branch surface that looks like this. So there's this circle's worth of what we call double points, which correspond to points that correspond to two surfaces coming together. And then we have more complicated situations where we have three surfaces coming together. And branch surfaces turn out to be a very nice way to describe foliations. And let's see, where do I want to be? Let me jump ahead. So one way in which we can get a lot of money out of, or a lot of worth out of branch surfaces is this this theorem due to Taut, which tells us that if our branch surface is nice enough, then it carries an essential lamination. So it's saying that if my branch surface is nice enough, and this is way too nice, but it's nice enough, I know that if I look at the branch surface, there's a corresponding lamination that fills up part of my manifold. And if the complementary region is nice enough, then I can also fill in the complementary region and extend this partial foliation of my manifold to a foliation of my manifold. And Gabay tells us that if we look at the complement of our branch surface, where by that I mean you take a regular neighborhood of your branch surface and you give it some extra structure. So you have parts of the boundary. So this is this picture, but think of it cross-eye. You've got horizontal boundary pieces. And you've got vertical boundary pieces. And so let's just thinking about in the complement of my branch surface. And if I was a better artist, I could quickly sketch the same thing for this picture here, but I won't try. You can think about what I've colored pink here is playing the role of what Dave called sutures, or annular sutures. And I'm not going to really say very much about them, except if we look at our previous example here, you could think about those purple annuli correspond to sutures. And we're thinking about our foliations are going to be a transverse to the purple and tangent to the white. So they're going to be transverse to the sutures, and they're going to be transverse to the complement of the sutures. Okay, so what we really want to be doing is saying, oh, okay, I've got this branch surface that's in my manifold, and it's got complementary regions. And we're very, very happy if the complementary region around something I want to do Dehn filling on looks like this complementary region right here. And we're even happier if every other complementary region, and that's a special example of something that's going to be taut, but we're even happier if all the other complementary regions are taut, because then Dave tells us we can just fill in the complementary regions with leaves. So we're going to play this game where we first construct a branch surface in the complement of a boundary component of our three manifold, and we're going to try to find constructions where the complementary region around the boundary or around some knot in my manifold is particularly nice. It's just a solid torus with some number of cusps, but whereby cusps are here, I'm thinking there are two, one corresponding to this circle and the other corresponding to this circle. So if we can find a branch surface that around the knot looks like this and elsewhere complementary regions are taut, we win. We have a taut foliation of our manifold. And so persistently foliar was, well, actually Delman, a long time ago, instead of taut foliations, we wanted genuine laminations. And so it was much more exciting if something was persistently lamina, which is the term that Charles originally introduced. But persistently foliar if every non-trivial Dehn filling yields a manifold that contains a taut foliation. And there are variants of this definition floating around because maybe we want to restrict attention to foliations that are transverse to the core of the Dehn filling. Here is a questionable slide that I just added in because I haven't talked very much about other constructions. But Charles has some really nice work where he uses most normal form to find foliation. So if you're looking at a particular example and you want something that's going to capture the geometry of what's going on, one game you can play is to use most normal form and think about what that means in terms of branch surfaces and play most normal form games. And Nathan Dunfield has this really nice construction using persistently foliar triangulations. Okay, so I'm going to start with this example. I'm going to start with my manifold just being the complement of -255. So we're going to jump up to an example that's a little bit more complicated than the earlier ones. And so I want to build it up, and I'm going to think about building it up as, you know, just like we began with circle and then arc, meeting just transversely, I'm going to describe all the surfaces that I'm throwing into this picture as meeting transversely, and then we're going to play this sort of smoothing game using the transverse orientation, just like we did when we went from here to here, beginning with those orientations which were plus before. So it's the co-orientations that tell me how I smooth things so that there's a well-defined tangent plane field. I go from things which are meeting transversely to smoothing things so that the object I have is a branch surface. There's well-defined tangent plane field everywhere. Okay, and I'm going to do this in this extremely concrete example. We're going to look at S3 minus the neighborhood of -255. And there's a tiny bit of history here. So before Heegard-Floer, there were these, examples that there was this notion that you would have a taut foliation unless somehow your manifold was too small. And we didn't really have good notions of what too small meant. And so there were some examples. Charles had done most of the Montesinos knots and talked about finding foliations in their complement. And then there were these ones that were left over that were kind of small. So we know that there's no way that we're going to find that -2n+1 is going to be persistently foliar, because we know that there are lens-based surgeries, say. So in particular, -2n+1 n positive is going to be something where the construction would fail. And so we looked way back when and we said, oh, okay, well, -255 is completely different, but we don't actually really understand why it's completely different. And then Heegard-Floer came along, and then, there were all these examples. So, Heegard-Floer, you can show these aren't L-space knots. And Cameron Gordon called one day and said, okay, Rachel, can you give me a foliation of this? And I thought of Charles, and I called Charles, and it was on our list of things we didn't know how to do. And the rule of thumb seems to be if there's a concrete example that Heegard-Floer tells us is not an L-space knot so far, but I mean the examples all have a lot of nice structure, you can find a taut foliation. So here's the game that we play. So here's your knot complement. Let's begin by just taking a blue boundary of a neighborhood of K. So we're taking a torus, and so we have this blue torus. And that's our first surface. So our first surface is this blue torus. We're then going to take this surface. So this is a spanning surface. And it's just, I get it by doing the, the checkerboard coloring of one of those two surfaces that we have from the projection. And we notice that it's non-orientable. So we notice that it's a non-orientable surface, but we're happy. We keep going. We want a co-orientable thing at the end. But as we go on our journey to find our foliation, we're okay with seeing some badness at the beginning. And for some reason, I guess I decided to just draw it bigger so that it would match what we did next. So the game here is now we're adding in a disk. And at the moment, everything is meeting transversely. We've got a blue torus, we've got a red surface, and then we've got a green disk. And I haven't included all that much information at the moment, but let's just focus on the boundary of that green disk. It travels along the Seifert surface over the knot, spanning surface, over the knot, spanning surface, over the knot, spanning surface, over the knot, spanning surface. And then it just goes underneath, and it skips these two crossings. So I have chosen, I tell you that I know how to smooth things if I tell you the co-orientations of everything involved. And I'm cheating a little here because I just decided, there's too much detail already. But in here, I should also be giving you a co-orientation on the blue T, and I'm not. So there is a co-orientation on the blue T that works nicely. But if you look just at the green is plus and the red is plus, when you do this sort of smoothing, you're going to have the red surface, the green surface came in tangentially, it's going to then be pinched so that the co-orientations work out, so that we have a well-defined tangent plane field, so we've got this well-defined co-orientation on my bronze surface. So we have this picture, and ignore that red that's also wrapping around at the moment. And now look at the orientations that I have talked to you. Oh, look at that. I don't know why that's happening, but it's kind of useful. So I've given co-orientation. I've given the co-orientation on the disk. Let's focus in on there's one place where something interesting is going on. And that's that right, oh dear, I can't figure out which one I'm looking at. Yeah, right here, this one. So we notice, forget that big red slash that's going through things. Focus in on the blue and the spanning surface. And notice that there's an arc of green that crosses from the knot to the knot. And I'm going to think about that green as cutting my spanning surface, and I've got a co-orientation minus on one side, and I've got a co-orientation plus on the other side. So if you think about what that means, I've got my surface I've got a little piece of my spanning surface. I've got this green disk that's entering in. And it's slicing through, and on one side I've got my co-orientation plus. On the other side I have a minus. That means that when you're thinking about the bronze surface that's corresponding to this picture, you have something like this. And then the green is just heading out. So we've introduced this, we've used the bronze surface to allow ourselves to change things. So at least when we're thinking about, forget that rightmost strand, which is also causing non-orientability concerns, we have this local co-orientation on the green disk and on the surface, and secretly also on the blue torus, which allows us to smooth things coherently, consistently. And if you look closely at these co-orientations and figure out what to do, to make things fit with these co-orientations, we will have introduced along this crossing of the knot, we will have introduced one of these cusps, one of these. So the thing I have marked C, you should think about, you started off with a perfectly nice, smooth blue torus, but a really boring one because, all sorts of compressions. And we've introduced one cusp where we have marked the C. So if you chase how the co-orientations force you to smooth things, and I couldn't think of any clever way to make that not painful the first time you do this. But you'll see that where you have a C, you can have introduced one of these, and forget the labelings A and B. They play a role in some dictionary I have. But the key idea here is that we've taken advantage of the non-orientability to introduce a different type of branch surface where we now can locally co-orient the spanning surface around the neighborhood of that disk. And so then now you can actually step back and say, oh, okay, what are these red things? They're not supposed to be red. They were Tuscan red, I think they were in my markers. So dark red, maybe I'll call them dark red. So you should think about, we started with T, and then we added in the spanning surface. Then we added in D1. Now we want to add in a D2 that fills up this other, if I took a fattened up neighborhood of my spanning surface, I would just have a genus 2 handle body. And so I've got 2 meridians for the complementary genus 2 handle body, and I added in the green, and now I'm going to add in a second disk that fills in the second hole in my genus 2. And the issue here is this is kind of difficult to see, but let's just go for it. And we're going to say, oh, okay, so morally, this is just a disk that's filling up that hole, but I want it to give me a branch surface that has taut complement and that carries laminations. So if you chase how the boundary works, this boundary is going to, the boundary of my dark red disk is going to cross the knot, and I'm not sure how to stop it doing this magnifying thing. Oops. Oh, dear, sorry. So if we think about this as it crosses, we don't cross that crossing. We cross this crossing. We cross this crossing. We cross this crossing, and then we run behind the surface, and then we have to somehow match up so that we don't have any other crossings. Okay, this is a way of matching it up if you can decipher well enough my picture there, which is no guarantee. You now will have introduced another C over here. So you'll have an evenly meridional branch surface. And if you look at the complement, you're just going to have a D2 cross I with the suture just being the boundary of D cross I. So this is one of these nice setups. And so we have taut foliations that realize all non-trivial boundary slopes, and the object I end up with is transversely oriented. So we've started with a non-orientable spanning surface, and we've ended up with an oriented, transversely oriented branch surface that is evenly meridional, and the complement is just a product. So we're good. So if we had to find that second disk every time, it would just be horrid. I mean, this is sort of the easiest example in which we would do this. And it's maybe not that horrid once you've had 10 minutes or more to think about it, but it's somewhat complicated. So just as a recap, we've got that the complement, we've started with this branch surface that we built up by taking T, the spanning surface, in these 2 disks. It's evenly meridional. There are no sink disks. So every non-trivial Dehn filling has a taut foliation. And the thing that saves us in this construction is that there's an inductive description of how you choose the D1 and then you choose the D2. So you don't quite have a nice taut-sutured manifold as your second step. You have something that's modeled on a nice sutured manifold, but you do have some sort of an inductive cutting process, which is a little less forgetful than a Gebai hierarchy, but which is tame enough that we can spot the D2 in the second step really, really easily. And that's what we did, and then we translated back to get the picture on the previous page. So one of the things that had seemed key to me for a long time is that, you know, when we were initially looking and we were trying to build things with a minimal genus Seifert surface, it just seemed like things were doomed. We didn't have a proof that showed that we couldn't do that. But it seemed very much that if we tried to constrain ourselves to branch surfaces that carried, slope zero surface, you might not be, you shouldn't expect to always be able to get, everywhere. You might be stuck in some neighborhood of slope zero, where I mean stuck meaning if I want to think about slopes that are strongly realized by a taut foliation, or slopes which can be realized by leaves of a foliation that meet the boundary transversely, you're going to fail. And I didn't really have a good notion of why that should be, and things were really difficult to prove. So I'm going to do an advertisement for Jonathan's talk. I think this is just an amazing result that he has. If you have a pseudo-Nosov flow without perfect fits, having a singular K-prong orbit, so we're in a situation like that in the previous example. If you think about this example, it was fibered, and if we think about the complementary regions of a stable lamination or an unstable lamination for the monodromy map, we have a single 4G minus 2 punctured gone. And the way in which your monodromy works is to go one click. So here, this is this notion, okay, the first return map rotates by L prongs, GCD L equals 1. So we're thinking about L as 1 in our example. And so there's an open interval of slopes containing the 1 over 0, so that you'll get a pseudo-Nosov flow with no transverse foliation. So, it's not quite the same statement, but it's a really nice statement that feels very much to be the right one. So this is just this note that, okay, if K is persistently foliar, secretly really I'm thinking about K fibered at this point, but so we've got some K that's persistently foliar, but not via branch surfaces that carry a minimal genus Seifert surface. Can we hope that there's a useful, non-orientable essential spanning surface so we can play some variation of the game in the previous example? And first, when I was thinking about this, I was like, okay, well, Nathan has these examples of knots in S3 without non-orientable essential spanning surfaces. And it happens, though, that these examples are all L-space knots, which might just be that these are the easy ones, so it was easy to come up with examples. But maybe there's something there. Okay, so our theorem is that if a knot has an essential spanning surface with certain nice structure, then K is persistently foliar. So this is a not particularly nice theorem because the certain nice structure is the properties are in a kind of ugly form at the moment. But let me just go through some examples where this game works. So if we have a Montesinos knot that's not an L-space, so we can show that any surgery, so that any knot that isn't an L-space knot is going to be persistently foliar. So persistently foliar, so we realize all possible non-trivial slopes. Same statement if we have a non-torus alternating knot. As long as we're not a non-torus alternating knot, we're persistently foliar. So every non-trivial Dehn filling gives a taut foliation that's transverse to the core of the filling torus. Let me skip that top one because it's too busy and it's the end of the day and a lot of people in the room, including myself, have jet lag. So, but let's look at the bottom one because it's easy to say. So I can ask myself, well, does K have a minimal genus Seifert surface which has got some band with at least 4 half twists that I've summed in there? Or somewhere I see a minimal genus Seifert surface in a disk and there's enough twists. Then we can show that the knot has to be persistently foliar. So in a sense, this made us very happy because this was the first construction we knew about where non-fibered made things easier. And there are other sort of instances in that example list where non-fibered made things easier. And the reason this made us happy was because this Ghiggini result, which tells us that if there's a non-trivial L-space filling, or if we have an L-space knot, it has to be fibered. So let me just end with another sort of class of examples where sort of the product pieces of the complement of the minimal genus Seifert surface in this case cause issues. So let's think about an alternating knot. And if you're someone who wants to construct taut foliations, the interesting cases tend to be the smaller ones. So we're thinking of well, in this particular example anyway, that rule of thumb is true. The examples that weren't really understood very well were the Seifert surfaces for which there's no separating among the Seifert cycles. So the minimal genus Seifert surface for the alternating knot came from one of the checkerboard colorings. So we have this projection of a knot, and it's alternating, and we're choosing the checkerboard coloring that corresponds to the oriented surface, so the Seifert surface. And now I'm pausing because I can't remember the original people who proved that those surfaces are minimal genus. I first learned through Dave's construction and...
So it goes back to Morse-Crowell, 1960.
Thank you. So we know that this surface is minimal genus for various reasons. And we also can, think about associating to that surface a graph where we plop down a vertex wherever we see a disk bounding a Seifert cycle and an edge corresponding to the twists. And that gives you a sort of cheap and easy way of representing the surface. And in the work of Gabais that I just referred to, he showed that, his proof that these were minimal genus was by giving a hierarchy, and the way you could get the hierarchy was you could see that if you thought about plugging each of those innermost cycles with disks, you could get a good description of after you'd done this disk decomposition, your graph would modify in a very simple way. So you would end up with a manifold with taut complement, and you could easily see that the complement was taut because it was just the complement of a minimal genus Seifert surface for an associated alternating link. So we can almost do that, except the problem is that when we play this game that allows us to change orientations as we pass through one of these arcs where the surface crosses the disk crosses the Seifert surface, we destroy transverse orientability in general of the surface. So instead of just adding a single disk and getting a nice graph condition that tells us we win, we have to add 3 disks. Well, really 2, but we add 3. And then again, the effect of adding those 3 disks is the same as the effect of playing Dave's game 3 times, where you add an innermost D1, an innermost D2, and an innermost D3. And so you've got the graph picture again telling you that the complement is a taut sutured manifold. And just to continue a tiny bit more, if you add D1 first, those arcs that are labeled with diamonds are the ones where we end up starting with my minimal genus Seifert surface like this and introducing a cusp in the minimal genus Seifert surface. So the transverse orientation we started with on the Seifert surface is no longer the orientation that we're considering on the Seifert surface. We've introduced a plus must go to a minus. And so then D2 is there to fix that. But D2, I can think about it can run over, the boundary of D2 can run over the D1, and in the way that we've got described there. And so then finally D3 is just to clean things up. We wouldn't actually really need it. And I think that's the end of the story for today. So thank you very, very much.
Thank you very much. Questions for Rachel? So I have a question. So is it known if Montesinos and the other class of knots, if they have a non-orientable essential spanning surface or not, in general?
Well, I guess the issue is the essential. So alternating knots, you always have the other checkerboard coloring. And then I would have to think for a little to make sure that I wasn't forgetting compressions or boundary compressions or something. Montesinos knots, I mean, again, you have all this structure where you can just change, one of the rational tangles to give yourself a non-orientable sort of. It's a sort of a two-bridge knot question, at least locally. So you're probably fine there also. We just didn't need to use it except for those cases. Yeah.
Yes?
Yeah.
So you mentioned about some pseudonymous of flows without transverse Taut foliation.
Jonathan's work. So Friday, really exciting talk.
Other questions? If not, let's thank Rachel and all the speakers today. So dinner will be at 7.